Okay, hi everyone. So this is the last lecture before the midterm, and then we should be able to finish this in 45 minutes. Okay, so you guys can go early. So let's come back to this potential well. The square potential well we discussed from last lecture. Previously, we say, okay, the infinite potential well, we solved the infinite potential well, but then that's not physical because you can't actually create an infinite barrier for electron. Okay, so what we do then instead is, okay, we let one side of the potential well to be finite potential. Okay, so this way you can imagine that if you have enough energy of the electron inside, then the electron can potentially escape. And in the last class, we solved the time-independent Schrodinger equation for this potential well. The result is quite straightforward. When x is smaller than 0, you have the infinite potential well, so that the wave function eigenstate is 0. And then inside the potential well, the solution is the same as before. It's a sine wave. Okay, the reason that you dump cosine is because this boundary condition. And then when it's in this this region, potential V knob, okay, you can also solve the Schrodinger equation, and then you will find that because we are only interested in the state that the electron is confined in the potential well, so that here there are actually two solutions. One is exponentially decay, the other one is exponentially increase. Okay, and the exponentially increased one will explode at x approach infinity, which is not physical. So you're left with this. Okay, so and if you plot them, okay, on the potential well, you will see, okay, there's a sine wave here, and then there's the exponential decay in this side. Okay, and then you can plot n equal 1, n equal 2, and then all the way up. And the only condition for this to be true is that you have to have En smaller than V knob. That way your electron would not escape from the potential well. Okay, and then we say that here for the eigenstate, you actually have three unknown parameters. One is obviously the eigenenergy we want to know. Okay, the most important thing in a Schrodinger, in a quantum system. And then the other two are these two coefficients, A and C, right? A and C. So for three unknown parameters, you need three equations to solve them. So the first one is, of course, for every problem is the same. You need to have a normalization condition for your eigenstate. Okay, and the second one is that we introduced that the Schrodinger equation, because of the Schrodinger equation, it has second order derivative, so that your wave function has to be continuous in the wave function itself and then the first derivative. Otherwise, the second derivative can go to infinity, and then the equation would, the left hand side will not balance the right hand side. Okay, so given that, then you will have wave function continuous all the way, but then you see that in this region within the well, it's a sine wave function, it's continuous, and then beyond that, beyond x larger than L, it's also exponential decay, that's also smooth and continuous. So the only thing that matters is at the edge here, at the boundary here, okay, at the boundary here. And then you can kind of imagine that because your wave function needs to be continuous, so that on the left side of the boundary has to equal to the right side of the boundary with your wave function. And the same apply to the first order derivative. Okay, and this gives you two additional equations in addition to the normalization condition. Okay, and they combine give you three equations to solve A, C, and En. And then I think well, normalization condition is a little bit boring, so we'll leave it there. I think last time we write down these two equations. One is that these two function equal to each other at x equal L. Okay, then you have a sine this L equals to this exponential, and then we also write down the second one is the first derivative of this is sine become cosine, and then there's coefficient in the front equal to the first order derivative on the right, well, of the exponential decay, right? Also the coefficient come out, and okay, you have these two equations. And if you look at these two equations, it's actually, if the only thing that you're interested is the eigenenergy, okay, it's the eigenenergy En. Then these two equations is actually good enough, right? Because you see they both have A on the left-hand side, C on the right-hand side. So if you take equation 2 and then divide it by equation 3, you can cancel A and cancel C. Okay, and then you get an equation that's that only have En, the unknown parameter, in it. And let's see. And before we go into actually solving this equation, solving for En, I want to briefly show you what we can expect. Okay, this is something very important when you try to solve something that's mathematically complicated. So usually you give it a little bit physical insight. So first thing is that how does En change with V naught? Right? If you have V naught going to infinite, right, that returns to the infinite potential well. Okay? If you have V naught goes to 0, then it's just a free electron with reflection on this side. Okay, so these two are very unique situations, and then you can kind of guess what will happen in between. So the question is, does En, so if we increase V naught or decrease V naught, does that lead to En to increase or decrease? Right. We can make this analysis and then see what to expect. And the easiest way to do this is actually to just compare this. If this is infinite potential well, then your wave function is completely confined in the middle, right? And then we know the fundamental state is a sine wave. And then now if you have a finite potential well on the right-hand side, then what will happen is that it looks like this, right? A little bit of tail going out. Okay, so this to here is V naught decrease. Okay, so the question is that simply by looking at these two graphs, can you tell which one has lower energy? Which state has lower energy? And this is go ahead.
On the right.
On the right, why is that?
Because isn't energy the integral? So the integral has less area on the right, so there's less energy.
Let me think about it. I think you made a good guess, but then probably it's not. Yeah. So the way to look at this is that, I don't know if you guys remember, the momentum equals to h bar divided by your h divided by your wavelength. Okay. And which one of them has longer wavelength?
The right one.
The right one, right? Because you extend beyond that potential well. So you have longer wavelengths, you have smaller kinetic energy, and then it ought to have lower energy. Okay, and this is just a guess. You can say, okay, there's also there's also potential energy here that matters, but then we're not. It's hard to analyze that part. So what you're only seeing here is, okay, when you lower the V knob, you increase the wavelength, and then you lower the potential, and you lower the kinetic energy. And you can keep doing that, then you will see, if you keep going lower and lower, right, then you have more and more extend into the outside of the potential well. Okay, so a reasonable guess would be, if your V knob decrease, then your eigenenergy will also decrease. Okay, and then let's see if this is true. When we calculate this, let's say this is lambda decrease. Lambda increase. Okay, and then to do this, we've already said that the thing that you need to do is to have equation 2 divided by equation 3. Right? You do that on both left-hand side and right-hand side. Left-hand side divided by left-hand side, right-hand side divided by right-hand side. And then A cancel A, C cancel C. Right? So what you're left with is, there's a coefficient here. And then sine divided by cosine is just tangent, right? Okay, equal to the right-hand side. It's also the same thing. You have a coefficient here. And then exponential divided by exponential is actually, I think it canceled. Yes, these two cancel, and then you're left with this. Okay, and then the next thing you can do is to simplify this. This is quite straightforward because you can see that the coefficient here is the same as here. Right, so you just multiply square root of 2m divided by h bar square on both sides. Okay, then this will come to this side. And then you can cancel a few terms here. You end up with this. Okay, so you get an equation that's only dependent on En. Right, you have a tangent, a field parameter times En equals En, and then there's a function of En. Okay, so the easiest way to do this is that if you know the mass of the electron, the size of your, the width of your potential well, then you just plot this as two curves, right? And then where they cross, that's your solution. And then, of course, something we can do is that we can double check. Okay. Oh, so first of all, this one only have numerical solution. There's no, you can't go one step beyond to get an analytical solution of En. That's not doable. Okay. So one thing we can see is that, okay, can we tell from this equation whether the eigenenergy decrease with the potential energy V naught, right? The way to do this is that, let's say if we let V naught goes to infinity, right? If V naught goes to infinity, this returns to the infinite potential well, right? And then we can see, okay, does that give us a valid solution? If V naught goes to infinity, then this is infinity, this is a finite number, so this term goes to 0. Okay, when V naught goes to infinity, this term goes to 0. Then what we have is tangent something equal to 0, right? Then we know that solution is whatever inside here. Okay, the tangent is a function like this. Right, it's a periodic function. This is x. This is tangent x. 0, pi, and then keep going 2 pi, and keep going. Right. So you know that when V naught goes to infinity, tangent equal to 0, so that the solution is 2m E naught, so En h bar square L equal to n pi, right? Equal to n pi. And then you can kind of rearrange everything, and then you will get En equal to n square pi square h bar square divided by 2m L square. Okay, and if you check the result, this is exactly the same as the infinite potential well, which means at least, you know, to this step, our math is correct. Okay, now let's take a look of how things will change if Vn decrease from infinity to a finite number, right? If Vn is now a finite number, then what happened is that, well, we still have Vn larger than, V naught larger than En, right? So this term is still positive, En is positive, so the right-hand side here is a negative number, right? It's a negative number. And then you need tangent something equal to a negative number. And if you move starting from tangent something equal to 0 and you move to tangent something is a smaller number, then you have to go this way, right? Tangent this is smaller than 0, so you have to go this way. So it means that for this equation to hold, your x equal to 2m En h bar square L, you know, has to be smaller than n pi. Okay, has to be smaller than n pi when E naught, if V naught is finite. Okay, it has to roll off this side so that you can get a negative number for your tangent. Okay, so this means your 2m En h bar square L square smaller than n square pi square. Okay, the inside, this side smaller than n pi. So this tells us that, okay, the previous physics analysis or intuition is correct, because when you reduce V naught from infinity to a finite number, your En has to be smaller than your eigenenergy for the infinite potential. Okay. And you might wonder, okay, why do I need to, like, can I just solve this in Mathematica or MATLAB? Why do I need to do this, right? So in reality, a lot of times, you know, when you, well, there are two reasons. Okay, the first is that in reality, a lot of times you don't need to know the absolute number. You just want to know the trend. And then, for example, if you want to increase the energy difference inside this potential well, and then you're wondering, okay, should I increase V naught or decrease V naught, right? That's a very simple question. And then, of course, you can solve the entire equation, but then that's just physical. Well, that's just mathematics. It doesn't give you any physics insight. The second reason, I think, I don't know if it's a joke or not, but UVA said a lot about that, how students need to become leader in the future. Okay, and then, but they never show you the way, right? Okay, so here's something. Okay, if you guys want to be a research leader in the future in a company or in a university, and then you have team member, okay, and then they submitting result to you, how do you know if you should trust their result or not, right? You can't just reproduce all of their calculation because it would take you forever, right? So knowing how to quickly judge whether a result makes sense or not is actually a must-have capability for so-called leader. Anyway, okay. Now, one thing that's beyond this mathematics, one thing that I don't know if any one of you think it's or have question on this is that if you look at this wave function, right, it has a tail outside this potential well, right? It has a tail here. Does that actually mean there's some probability that we can measure electron here? So the electron has energy less than the potential well energy. So classically, electron cannot go outside. But then here, we show that, okay, there's actually your wave function is not zero here. It seems that by the postulate of quantum mechanics, right, the wave function amplitude square means that the probability density of you detecting an electron at that position. So does that mean that sometimes the electron will go out of the potential well? Can anyone make a guess?
I want to guess yes, but like it's very improbable.
Mm-hmm.
But I don't know.
Yeah. Okay, but then it from math it makes sense, right? Like that's what the quantum mechanics tell you. Okay. Have you guys heard about quantum tunneling? No? So quantum tunneling says is that, well, there's a famous, well, yeah, you guys are too young to know that. There used to be a show, Big Bang Theory. There's Sheldon says something that, okay, my probability of going through this wall is not zero because of quantum tunneling. Okay, and the idea here is that yes, from classical point of view, if everything is classic, then you can never, your electron here, because your energy is small, you can never be able to jump out. Okay, you will never be able to do that. But then because your electron is a wave, the wave actually can penetrate things. Think about it, okay? The reason that you have Wi-Fi is because it's wave, right? If it's, well, because of the wavelength, okay? Not just its wave, but because of the wavelength. Imagine if your Wi-Fi signal is a little bit of, bullet ball, okay? And then it can never reach you from the router, okay? And then also it's the same reason why you can have a radio, walkie-talkie, and that's a longer wave. That's actually a longer wavelength, so you can have a longer range, right? The Wi-Fi, and then now people are talking about 5G and then potentially 6G, and then some professors are actually working on light Wi-Fi. The problem is that if your wavelength is shorter and shorter, it becomes more and more like a particle. Okay, it's the same as here. If you think about it, if you lower this potential well, then the wavelengths become longer and longer, and then you have more portion that penetrate into this, potential well position, so that you actually have more probability of going out. Okay, going out, and this is called quantum tunneling, okay, or wave tunneling. You can understand this. Okay, quantum tunneling, and this is real. Okay, this is real. I don't know if you guys, I don't know if anyone taught you the what's the physical limitation of the transistor. okay, why the Moore's law is no longer going down. Right? I'm not sure if this is part of the EC education. The reason, part of the reason is that the transistor now is becoming smaller and smaller, that it actually go into this region now. Okay, when you're smaller and smaller, your barrier, okay, the potential well to hold your electron in certain device in one transistor, this V knob is going down, right? And then you have more chances your electron will penetrate or tunnel through your one transistor to another transistor or to another unit. And so that's why there's actually a physical limit, okay, to how small you can actually make the transistor. Okay, and of course they don't say it that way. I think the part of the problem is that when you're going smaller, and then also you have your device is less immune to defect, right? Because defect will make your V knob different from design. You can make a design that make the quantum tunneling effect not affecting your performance, but then because it's very small, then the V knob actually fluctuate in your fabrication. Okay. Now,
I have a question.
Yes.
If you can roll it. Is it correct to think of it as sort of like the required energy to be in that specific location, like the place where V naught is where it is that saying like the electron needs to have like at least that amount of energy to like be in that place? But
yeah, that's a good question. So you're thinking in terms of classical way, right? Like in classically, let me erase some of this so that we have. Yeah, we should talk this in more detail. So classically, okay, if you have an electron here, and then because the potential energy for here is 0, right? So whatever energy you have inside the potential well is your kinetic energy. And then classical mechanics tells us that because of energy conservation, right? If your electron escape, even it's sitting still there, you have energy greater or equal than V naught, right? If you're moving, then you're greater than V naught, right? So classical mechanics tells us that your electron cannot go from here to here if your energy, kinetic energy, is smaller than your potential barrier energy, right? Because if you go from here to there with energy smaller than this, you violated the energy conservation, right? Okay. What quantum mechanics tell you is that just screw that, right? It doesn't matter. Okay, it's a wave. If you actually try to measure, okay, if you have a detector, which, well, this experiment itself is difficult to do, okay? If you have a detector, you want to say, okay, do I have an electron here? Okay, or do I have an electron outside the potential well? Then what you do is you calculate the probability of electron larger than L, and this is just an integration from L to infinity, and then your state, amplitude square, and dx. And clearly, because this is not 0, so this integration is not 0. Okay, so you don't need the energy to be larger than V naught to have your electron escape. Okay. Okay, and this is a little bit, well, you might wonder, okay, why? Then how is the energy conservation satisfied, right? That's an obvious question. How can you just say that you can violate energy conservation? So in quantum mechanics, this is important, is that energy conservation is not preserved as single measurement. Energy conservation is preserved at expected value. So if you measure, let's say 10,000 times, okay, electron can be here, can be here, can be here, can be here, can be here. Each position, they will have a different energy, right? And then if you average all those energy, you can see that average all those measurements, you can see that the measurement result is the same as the energy you save inside. Okay, so I know this is not the correct way to think about it, but then you can think about it in every measurement, there's some uncertainty there. Okay, so you don't have to preserve the energy conservation law, at every measurement. Okay, just overall, when you average everything, the energy conservation has to be conserved. Otherwise, think about it. If energy conservation is not conserved when you do thousands of measurements, then you will be able to produce something that's observable in a macro scale that violate energy conservation. That has never been observed before, right? If you say, okay, one electron can go this way and then violate energy conservation, but then if millions of them can do that, then you have a current, right? and then you will see that. So that's not possible. Okay. Yeah, I guess that answers your question, right?
Yeah, it's just kind of weird.
Yeah. And I don't know if you guys live in the UVA dorm or not, but if you're in a UVA building, actually there's something that can do quantum tunneling inside your building, which is a little bit, you might not think about it in that way. So the most commonly known tunneling device, only costs about $10, and then you can buy it online, and that's actually 2 fiber. It's called a fiber coupler. Okay, so what it is, fiber, probably you guys have heard of it. Fiber is a piece of glass that confine light and then transmit light, right? That's the reason why we have internet. Okay, and then here it's not quantum tunneling, but it's Maxwell wave tunneling. It's the same thing. If it's a wave, you have potential well, then you have tunneling. So this device, okay, we have, I don't know, we have 20 of them in our lab, and then probably for a lot of the routers, fiber cable routers, like the really high-speed internet router, that you actually have some of this inside. So what it is that, okay, light is wave, right? So it's not perfectly confined inside the fiber. So there will be a little bit of, like if you look at the distribution here, there will be a little bit of tail, going out, just like here, right? There will be a little bit tail, exponentially decay. And then this has actually been discovered like hundreds of years ago. Well, not hundreds, 100 years ago, because you need Maxwell equation to discover this. And this is called evanescent wave. Okay, evanescent wave. And then when the photon travel to here, and then part of the evanescent wave overlap with the next fiber, right? The next fiber also have evanescent wave here. Then the photon actually has some probability of going from this fiber to the other fiber. Okay, although those 2 fibers actually never touch each other, you still have some chances of photon coming from one fiber to another and another to this one. Okay, and this is coming from, classically people call it evanescent wave. Okay, and then in quantum mechanics called quantum tunneling. Okay, so as long as something is a wave, you can do that. So in the past, people know that light can do this, because light is a wave. With quantum mechanics, now people know that electron can also do this. Okay, and in principle, you can do this. Okay, but your wavelength is very small, right? So the barrier that you can go over is actually very small. Okay, you guys did this in the homework too. You roughly know what's your wavelength, and then you roughly know if there's a wall you can tunnel through, how thin that wall has to be, and that wall has to be like 10 to the minus 36 or something. Okay, and then this is exponentially decay, right? So if the wall is becoming thicker and thicker, your chances of tunneling through is exponentially drop, right? So I know none of you will be stupid enough to do this, but don't try. Yeah. Okay, so a reasonable way to kind of convert this in a quantum mechanical version, this is called coupler 50. Well, it's called fiber coupler. You guys can search this. You can actually do a quantum experiment with this fiber coupler. You just, instead of sending classical light wave, you just send a single photon, which is a quantum object, and then it would do this tunneling. You can consider single photon similar to a single electron, and then you will see this quantum effect. And it's actually quite fun. It's like if you send one here, one there, there will actually be a quantum interference effect called photon bunching. Is that the photon will, two of them show up here or two of them show up there. It will never be like one at each side. Okay, it's a special interference effect, and then of course we won't talk about it here. And if you try to understand this system in terms of potential well, then one thing you can do is that you can kind of draw it in this way. Okay. All right, so the photon, okay, they can't go beyond it. They can just go into free space. So you can see, okay, the left side and right side. If it's an electron left side and right side, you can have infinite potential well, infinite potential energy. And then in the middle, there's some barrier. Okay, there's some potential that you need to overcome to go from one to another, right? So this is V knob. So if your electron, okay, it's on the left, then your ground state will look like this, and then exponential decay. And then if your electron is on the right, then also it will go with this and then exponential decay. And you can see that theoretically they will always overlap a little bit because you're never absolute zero, right? It's just exponential decay. So what will happen is that your electron will have some chance to go into the middle and then go there, even when your energy is smaller than this barrier energy. Okay, even when you have that. And so this is called quantum tunneling. Okay, and then this is an actual effect, and then people have measured it in experiment, and you can also see that with the cheap fiber coupler. Okay, any questions? No? Okay, so that's actually it for today. And then next week, because it's midterm week, so we will talk about something that's difficult but not 100% required in this class, so that you can pace yourself, and then the homework will be a little bit of homework but not a lot, so that you can have enough time to do your midterm. Okay, I'll stay here for a few more minutes, and that's it for today.